Students, now we move to one of the most fundamental and beautiful concepts in electrostatics, the electric field. If Coulomb's law tells us how charges interact, the concept of the electric field explains why interactions happen at a distance. Understanding electric fields deeply is the key to mastering the entire chapter. Let us begin. In physics, we avoid the idea that charges act on each other through empty space. Instead, we say, a charge modifies the space around it. This modified space is what exerts force on another charge. This modified space is called the electric field. It is the force per unit charge. This is not just a definition. It is a completely new way of thinking. For a single point charge question, E equals kq over r squared. It decreases with the square of distance. Its direction is radially outward for positive charges and radially inward for negative charges. This radial symmetry is crucial for Gauss's law later. Electric field has magnitude and direction. When multiple charges are present, E net equals sum of EI. This is simply the superposition principle applied to fields. One common mistake students make is adding magnitudes alone, but fields must always be added vectorially. Michael Faraday introduced the idea of field lines to visualize electric fields. The rules are: field lines originate on positive charges and terminate on negative charges. They never intersect. Density of lines represents field strength. Lines are perpendicular to the surface of a conductor. A uniform electric field is represented by equally spaced, parallel, straight lines. This concept is essential for understanding motion of charges in fields. We often deal with systems like charged rods, charged rings, charged disks, infinite lines, sheets, spherical shells. In all such cases, d equals k dq over r squared and then integrate. But symmetry often allows us to skip integration in JEE Main. Inside a conductor, electric field is zero. This is because charges rearrange themselves until internal fields cancel out completely. This leads to electrostatic shielding, used in Faraday cages, metal enclosures, and sensitive electronics. We define the electric field using a test charge, but the test charge must be extremely small so that it does not disturb the original field. This is a key conceptual connection. E equals negative dV by dx field is related to the slope of the potential graph. If potential decreases rapidly, field is strong. If potential changes slowly, field is weak. This relation is frequently asked in JEE Advanced. Students, this concept of the electric field is the heart of electrostatics. If you truly understand fields, the rest of the chapter, potential, dipole, Gauss's law, capacitors, all becomes intuitive. In the next topic, we will explore electric potential, the energy-based viewpoint that simplifies many complex systems.